Hello, and thank you for joining me for the Python part of our first data analysis bootcamp. Really, this is just an intro to Python data analysis. I'll make available the data set for this class. This is just a penguins data set, and we're going to go through here. So we have our data set here. We have our standard, and here we have our standard data science libraries: pandas, seaborn, matplotlib, and numpy. Importing the data from my GitHub reservoir. And looking at the data just to get started, we have a few different species, islands, we have the different lengths and statistics of our penguins, and we have their gender, male or we have 344 rows and 7 columns. Looking at the dot shape, an attribute here. So when we look at that, are there any any null information in our data set? So we run df.isNull. To show you what df.isNull does, it creates a matrix, a data matrix of a data frame of trues and false values. We use sum. By default, it goes across the columns. So it's going to sum up all of the values. Falses are equal to 0, trues are equal to 1. So we're able to sum up all of the true values, the times that it is null, and get a good sense of how quickly or how many null values we have in our data set. And you can see here, we got a few, not too many. A good idea is always to look at the .info. Data types are just so important. They affect many of your statistics, and we really want to understand what they are so that we don't run into problems in our later analyses. Python, kind of a sub way that we communicate with Python is the data type. So we really need to make sure that we understand them to prevent us from running into errors and to make sure that Python understands what we're trying to do at each step of the way. So to kind of for this class, I really wanted to highlight the effect of taking a sample, concentrating on that sample. So we have 344 rows in our data set. So if we look, I looked up on the internet and there were roughly 20 million penguins in Antarctica. Okay, so that's a lot. So we got a sample of 344. That fill up that pandas environment, no problem. Lots of penguins, but still just a very small sample. To kind of simulate the effect of taking a sample, what I wanted to do, this is only a fraction of a percent, a very small fraction of a percent, but what I wanted to do is take 2%, just as an example. So if we take 2% from our data set, and we'll pretend that our data frame is like the full population of pandas, and the sample that we take is the collection of our data set that we took today. So if we take 2% of our data set, that's only 6 rows today, but that will work for our evaluations and to understand how much our data can change just by taking a sample. That's really important to keep to heart. It's just that our data set, the statistics we get are going to change, are going to be different than the population. So we need to understand that variation that's created through the random sampling process. Okay. If we wanted to take the mean of a column, what we do is df column name dot mean, and we can get the average mass. We want to take the mean of all columns at once. We can go to df dot mean and take a look here and to show you what that looks like. Do sample one dot mean right here. What we're going to do is we're going to see the mean of the bill length, the mean of the bill depth, and each numeric column. Okay. What I did here before I took that sample one, what I do is df dot sample and sample size. So sample size is up here, it's the 6. So we're getting 6 rows. And what we can do is just to see then how much the mean is changing by each one of these columns. You can see changes quite a bit sometimes. So bill is 40, 45, 42, quite a bit. But let's look at all those together so we can actually make a comparison. Here I'm going to use pd.concat, use a list of the data that we want to put together. So we're going to go mean sample, mean 3, or sample 3 mean. And cross the axis once. I'm going to stick them together horizontally. And the next row, all I'm doing is putting the column names. So change the column names. If we didn't do this, we'd see 0, 1, 2, 3. So not super helpful, but if we can give the column names a little bit clearer for our end user to be able to. Okay. So let's create one sample. Let's do it 50 times and really start to get a sense of this variation that we're getting. So we can see that there's a lot of variation here, quite a bit in the bill length, a little bit less in the bill depth, but let's really start to understand this variation that's caused through the resampling process. Okay, so I'm going to create a blank data frame. A classic for loop or for loop syntax is to create a blank list before you go into your for loop. And so here we're doing with a data frame, we're going to create a blank data frame that we're going to fill up as we go through our loop. It's a little bit different than the list, but it works very much the same. Okay? So we're going to go for, I'm going underscore. The reason I put an underscore here is because I don't intend to use the iterable variable in my loop. So I'm just going to say blank because I'm not really using it in this one. So for blank in range 50. So I'm going to creating a list of 50 values. I'm just going to be repeating this 50 times. We get a sample of my sample size 50 times. I'm going to take the mean 50 times. And I'm going to stick it into my df means data frame 50 times. Get a sense. And so you see all these errors. It's not necessarily something we need to know today. I've seen this many times. So it kind of gets a little bit boring. So if I didn't want to see that every time, the way that we can turn off our warnings is we go import warnings. It's letting you know about something in the future. It's going to be changing. Good to know. You don't need to see it every time, right? So import warnings, warnings.simple filter, and just ignore, right? So we turn these off. If I were to run this again up above, you'll see. There we go. No more warnings. Makes it a nice cleaner workbook for us to share. So because we were sticking things together vertically, or sorry, horizontally, we have 4 rows and 50 columns. So just to get them in the sense so that we can plot this and work with the data like a typical data frame, when our column names at the top, we can just go dot T and tilt our data frame 90 degrees like we have. And so it's good. Let's actually just save that like that so that I can use it, work with it when we do our plotting in the next stage. So here what I'm doing is df means. I'm just saving it as this tilted image. So what I'll do then is space here. So sns.hisplot data equals df means, and then x equals bill. I'm going to get the population mean from the original data frame, all of our population, the whole 20 million, our simulation 344 samples that we're using to simulate the 20 million population of penguins in Antarctica. Okay. Here what we're doing is we're going to take min. So we're going to, sorry, let's go step by step. And then what I do is I plot a vertical line of the mean of the population. So you can see we are centered, our data is centered around that. And then what I'm going to do is I wanted to understand what the confidence, one of the things about this resampling is we can build confidence intervals. So we know our population is this, but we wouldn't know that if we were just taking a sample. We would have to resample this and we can get a sense that our data is in a certain population average is in a certain range. And by this resampling process, we're simulating that. So we'll be able to say, if I want to get the NumPy percentile, the 5th percentile to the 95th percentile, I can get a sense of how much data falls within that 95 percentile. Okay. And so every time I run this, it's going to be a little bit different. So if I were to rerun this sample here, the loop up top, I will get a slightly different sample. This is a resample. Make sure I tilt it again this way, and so it's going to be different every time. And now we have, just noticing at the bottom, our confidence interval where we could be 95% population mean is between 40.23 and 47. So although our average is right here, we're confident that our true average is in this range, not this full range right here, but 40 to 47. I'm going to do the same thing with build depth. Here, and again, we have our average, we're 95% confidence in 5 to 18. And then looking at our confidence interval of flipper length, again, 199 to 210, so a bigger range here. And confidence interval for our body mass. So you can see it's centered around where the population center is, but that doesn't really mean, because we may sometimes get a sample down here. And so if we got the sample right here, we need to understand how much, or have a good sense of how much variation there can be collected just in the collection process that's created. We don't really have access to this statistic of randomness in our data frame, but it's there. It's kind of, it was created in the collection process, the sampling process. It's just not visible. So we just need to understand that it's there, and this is going to highly affect how we interpret our results and the understanding that we can take away from our mean or correlation that we are understanding in our data analysis. It's really crucial and important. to think about stratified resampling. We'll get a lot more into seaborn and how to use all the cool little things that we have access to with seaborn. Yeah, one of the main reasons that you, well, not main reasons, but a really powerful thing that we have access to in seaborn is this hue argument. It's going to change the color of our distribution by the color of the gender. Sorry, by the gender. Okay, so male and female here. Three here. So this is a quick little way to view the hue, kind of stratified resampling done on the spot, but not exactly really well. This is just splitting the data frame into color coordinating our data frame or our distribution. Let's actually do a resampling process and see if we can get a better understanding of this. So here what I'm doing is I'm going to create a female distribution. I'm going to do the gender of the female column, or the sex is equal to female. And what this does, if you run this, this creates a true and false Boolean column. And if we use that in the first square brackets after our data frame, we can select just those rows that were equal to true. Same thing for female and male, and we get then 165 and 168. Here what I'm doing is I'm doing the same loop that I did up above. I'm doing it for two data frames now. So female and male. And what I'm going to do is I'm going to sample for female, sample for male, get the mean for the female, get the mean for the male, and I'm going to concat those both into the blank data frames that I had up above, and then do that 50 times over, just like we did up above. Do the same thing here where I flip these a little bit on 90 degrees, just so they're a little bit more data friendly, and we have our column titles at the top. Okay, so I'm going to plot the histogram of the males, histogram of the females data frame of the same data set. And then what I'm going to get is the confidence interval for the female, or sorry, for the males, and then the confidence interval for the min and the max percentiles. And then I'm plotting it out right here. And just to know, I just kind of skipped over this, but so I'm putting the min here, what I'm doing with this little, I'm doing an f string right here. And that allows me to put a variable into my string and not just print out the word min, print out what's inside it. And then this :2 is saying 2 decimal places, a floating point number with 2 decimal places. Okay, so it just cleans it up. If you don't do this, you get a really long number. So this gives us a sense here. So if we see now on the male population is 42, the mean is between 42 and 49. The female population is between 38 and 45. As we can see, there's just a lot of overlap. So it really couldn't be any sure in any real sense that these are not from the same. Maybe a little bit confident here, but there's still a good amount of overlap. There are some outliers here for the female that are way over here to the left, but so maybe there's a chance, but really you can see that because the confidence intervals are not significantly, but overlapping with a good range, that we would have to be a little bit skeptical. Would have to be a little skeptical that there is really a difference between the male and the female population. It's very likely, but we're still not 100%. We couldn't statistically prove, but we can still get a better sense than just does it pass a hypothesis test. And we'll come to that in a later class. Okay, and so looking at here, we're seeing now the build depth. And you can see here, we have the min is 15 for male and the max is 19 for the confidence interval and the female. Again, we have quite a bit of overlap in this one. You can see here, and that's really amplified here. There's really some outliers in this female population right here, but the bulk of the female population seems to be very highly overrated. So, and this is a good point, even where the population is, or even where the confidence intervals are not exactly significantly, they're kind of half and half overlap. I think seeing this sampling gives us, visualizing the sampling process gives us so much more detail than just a simple confidence interval or even a hypothesis test. A p-value of 0.05, but what is the p-value of 0.06? What does that really mean? Okay. And this is a good way to see this. You can see that, oh yeah, well, we don't have that much overlap. Really, we can see that the bulk of the female population is really sitting on top of where the male population would be. This gives us some insights into how confident we should be in the difference. I would say here, I would say very unlikely that we would be confident, but there's also an interesting cluster or something of the female population that would be worthwhile to explore a little bit. Okay, and going here. So doing the same thing now for flipper length here and taking this. and we have 96 and 89. So it is, again, it's a lot of overlap, but you can see here now lots of the female population is over here on the left, not so much in the range that's overlapping. There still is a good amount of range, but getting a little bit deeper understanding of this sample and how much it would affect our population, how much the range could change. We might sometimes get a female average height here and a male average height here, but lots of the time we'd expect it to be the same. But we know they're still not exactly the same. As we look at this, we can still see there's a substantial difference between these two populations. And then looking at, we have here the body mass, getting a good sense here. Really, there is just so little overlap here, only goes to 44 is the minimum, and to the maximum is 4,300 here. So it does say that they go over a lot, but you can see here there's a little skinny tail. It's not super skinny, but it goes to kind of little tail where they overlap. So for this one, I would be very confident that we would expect to see a female that is much smaller than a male. And we know kind of how mammals work, I guess. That's not super surprising, so we would expect to see that, but it can be something that we need to be aware of. I shouldn't say mammals, we should be aware of birds. Generally, the males are bigger, and we really want to see, but this tail that sometimes crosses into it, it's not really a bulking, it's not like a normal distribution, it's a little tail that crosses into this. And so you can get a better understanding of what are the chances that we would expect to see. Okay, and here you see direct features have associations. So we're looking at correlation. You see a correlation matrix here, and we're able to quickly tell if the bill length in millimeters has a correlation with the bill depth. And we see the bill length has a correlation of 1 with itself. It's perfectly correlated. With bill depth, it has negative 23. Flipper length, bill length has positive 65 and then a positive 95% with mass and we get a sense of what the relationship is to the feature. But as I said, we can expect these on a deeper level, and a good start is just with the scatter plot. So the way we do this very easily with the pandas plotting function is df.plot, kind equals scatter, x equals bill length, y equals flipper length, title equals, and we put a really handy feature about pandas is we can put our title right into the plot, very quick and easy, and we can also change the figure size. A little bit more difficult in seaborn, not difficult in a sense, it takes a little tiny bit more to do in seaborn. And getting a sense of the correlation, and you can see here there is a lot more going on between these two variables here than just a, there is a negative correlation between bill depth and flipper bill depth. Bill depth and flipper length. Sorry. And so looking at the correlation, so you can see there's a lot more going on between this correlation. If we look at the correlation, it's a negative 0.58 correlation. So you can see this shows a negative correlation here. And so there's obviously a lot more going on here. This looks like there's two clusters or something. So it'd be something worthwhile to inspect. So now looking at the proportion of each penguin living on each island, island. And so a quick way to do this, really what I need to do is I need to count, just really from one column, I need to count it each time they're from each column. So what I'm going to do is I'm going to go df.group by island and species. Okay, so I'm going to group by island and then species to get a sense of the island and the species living on each island. Okay, I only really actually care about one of these columns. So I'm just actually going to be selecting from this data frame that's created in the group by value, I'm going to select just the sex column, really I picked just one of them. I'm going to create a pie chart. So generally in data science, they have kind of a not strong love for the pie plot. And that's because our eyes just are specifically not good at seeing the proportional difference. We can tell one's bigger than the other, but we have a very, and it's just our eyes, I have a very hard time at telling the exact amount of how much one is bigger or smaller. So you can see here 13% here, 14%, that would be very hard to see. The answer to really make this a little bit more usable is to note our plot right here and really put the percentages right here, make it a little bit easier for us to read and really understand that the purple is, although only a little bit big, not even a full percentage, it is bigger. Okay. I think we could do a little bit more to kind of highlight things. Some cool things that we can do in the pie plot is we can explode one of the layers. So I'm going to say I want this one to be separated by 15.15 versus 5, 5 or 0.05, 0.05 here. Gives a little bit of spacing and really steps it up a little bit. So just to show that we can do that, a little fun with the pie plot, and we have a little bit more fun. Okay, so I think this looks a lot better if we add just a little bit of extra detail to this and really adding a black line. plotting in pandas or in Python in general is it's easy to do. To do the formatting videos can be a little bit more work than you would expect, but it's really great practice doing some more higher level Python techniques right where we can see them happening. We can see the results of our Python coding in the moment, and we can have a lot of fun with this while we're practicing more complex things in Python while we're doing our data analysis. So this is a great way to practice some more complex things in Python, and we'll see a whole bunch more examples as we go through this. What I'm doing right here, I'm doing the same thing that we saw right above, and I'm just going to save this as an object. So it's typically called AX. In the next line, what I'm going to do is for W in ax.patches. This creates a list of all of the wedges, the parts of my plot. So this patches is showing us the list of the items in our plot. I'm going to go W, so wedge dot set with line width, and then set edge color to black. Put a title on this way. This way I can add a little bit of space before and after. I can change the font size, and I can make the title bold versus doing the title right in pandas font. A little bit more powerful. Notice that I'm doing this with PLT, so matplotlib. Pandas is made with matplotlib, so it is meant to kind of work this way that we can do this, we can call this on a pandas plot because pandas really is matplotlib. So if we want to do some extra formatting, we'll often need to use PLT matplotlib to do so. Okay, I'm just turning off the label on the left-hand side as well. And we get a nice little plot here. It looks quite nice. And it adds a little bit of texture. Some people still don't love the pie plot, but I think this really highlights if we wanted to say focus on our presentation, focus on the animals from the Biscoe and then the Adelaide, this group right here, and really talk about 13%. Maybe we go on to the next slide and we highlight a different section. Really powerful little technique, something really cool that you're not able easily to do outside of Python. So thank you so much for joining me for our first data analysis bootcamp, and I will see you in the second.